Welcome to week 5 problem of the week. I'm going to give two examples of a surface integral and also show a volume integral, focusing on the cube and on the cone. We're going to start with the integral over the cube. This is one of the problems that we had as a problem in class. We want to integrate over the surface of the cube of side A with a vector valued function f of x, y, and z, which is the exponential of minus x minus y minus z, times x multiplied by the unit vector in the x direction plus y times the unit vector in the y direction plus z times the unit vector in the k direction. There's 6 faces to the cube, so we actually have 6 surface integrals that we have to do. Each surface integral will go over one of those faces. We're going to break it up into 3 different scenarios. We're going to start with the front and the back surfaces. The normals here are I and minus I, and the surfaces are denoted in pink. Note there that the coordinates are given in units of A, so we're going to have to multiply those coordinates by A to get them in the actual units that we need. And let's look at the integral at the bottom. So the integral at the bottom, the integral at the back. The integral at the back is occurring where x equals 0, but x appears in the integrand, so we're going to get the integrand evaluated at x equals 0, which is 0 because x equals 0 there. So that integral from the back isn't going to contribute. The integral from the front, when I take the dot product of I with I get 1, so that's going to give me an x. X on the front is equal to a, so I'm going to get an integral over dy and dz, because those are the area elements. Those are both integrals will run from 0 to a. E to the minus a minus y minus z times a, because I have to set x equal to a because that's the equation for the front face. Now I can pull the a out of the integral, I can pull the e to the minus a out of the integral. I have 2 integrals that are exactly the same, and when I evaluate each one of them I get 1 minus e to the minus a, so I get that whole thing quantity squared, and that's the result of the integral over the 2 pink faces. So we're going to move on next, and we're going to consider the right and the left faces. Here the normals are j and minus j, and the surfaces are denoted in purple. Once again, the surface on the left, which has the minus j normal, that's evaluated at y equals 0, and so that integral is going to vanish because it's proportional to y. The second integral, which is the right-hand side, is evaluated at y equals a, and if we look carefully, it effectively is the same integral as the one that we just did, and indeed if we go ahead and evaluate it, we actually get exactly the same answer, a e to the minus a times 1 minus e to the minus a quantity squared. Alright, we're nearly there. We still have the top and the bottom to do. Here the unit vectors, the normals are k and minus k, I'm sorry, that's a small typo there, and the surfaces are in green. And once again, the bottom one is evaluated at z equals 0, so that's going to give 0 result for the integral, and the top one is evaluated at z equals a, and lo and behold, it's exactly the same integral that we've been doing for the other 2 cases. When we evaluate it, we get a e to the minus a, 1 minus e to the minus a quantity squared. And when I add all 3 of those together, I get 3 times a e to the minus a, 1 minus e to the minus a quantity squared. And that's how we do that surface integral. So once again, just pay particular attention. You have to focus on identifying the unit normal vectors and taking the dot product of those normal vectors with the vector valued function, and using all the knowledge that you have about those different vectors and what their dot products are. You then will get the scalar integrand, and it usually then is still a multiple integral, and you just have to evaluate each dimension of that multiple integral until you get your final result. All right, we're going to move on now to what I think is a somewhat harder problem. It's going to be looking at evaluating the volume by doing a surface integral over the cone. We're going to be using this really interesting identity that comes from the divergence theorem that says that if we integrate the vector field f equals r over the surface of any object, but in this case we're going to do it over the surface of a cone, and we multiply that result by 1/3, then that is equal to the volume. And we went over the derivation of that in a lecture, and here I'm going to show an example of how that works with the cone. So let's focus first on the bottom end cap. There the normal vector is in the minus k direction, but because r dot minus k is equal to z, and z is equal to 0 on the bottom surface of this cone, that integral is going to be 0 because z is equal to 0 there. So the integrand will have a 0 multiplying something, and the 0 trumps everything will give me an overall 0 for the integral. So I'm only going to get a contribution from the slanted part of the cone, and now I have to integrate over that slanted surface. So for the slanted part of the cone, we're going to be using cylindrical coordinates, and those are denoted by z, rho, and phi. The area element for the slanted curve is rho d phi. That's the area element that is in the perpendicular direction. I can't illustrate it on the page, but at this point it would be located pointing into the page. And then I have to get that slant height. And if you look at the triangle at the top, you can see if I have a dz and I have a slope angle or slant angle of alpha, then the element ds is equal to dz divided by sine alpha. And so if you give me alpha, I can determine what ds is, and that's the other part of the area element that I have to put in. Now, by looking at the geometry of the cone, because the height is h and the radius is big R, I can immediately work out that sine alpha is equal to h divided by the square root of r squared plus h squared. The second thing we have to work out is the normal to the slant at the location rho phi, and I've illustrated that for you with the red vector coming off of the slanted part of the cone. It turns out that this is equal to h times e rho being a vector that is parallel to the green vector rho, plus r times ez, e hat z being a unit vector parallel to the orange vector, which is telling me the z coordinate. And you have to now carefully work out this geometry. You find it's going to be h times rho plus big R times ez. And then I have to make it a unit vector, which means I have to divide by the square root of, that should be big R squared plus h squared. So using the fact that the vector r is equal to rho e hat rho plus z e hat z, it actually has no e phi dependence. That tells me that r dot n is going to be rho h plus zr, and that will then be divided by the square root of big R squared plus h squared. Now that is a component that's going to go into the integrand, and the final thing I need to note is that the value of rho is determined by whatever the value of z is. So when z is equal to h, rho is equal to 0. When z is equal to 0, rho is equal to r, and it's a linear function, so I can just construct it. Rho of z is equal to r h minus z divided by h, and you can easily verify for yourself that that is a linear function that vanishes when z equals h and is equal to big R when z is equal to 0. Now we're going to put this all together to get out the integrand, and there's lots of terms. So we have the volume is 1/3 the integral over the surface of the cone of f dot n hat, and that is equal to 1/3. Now I have to put in my surface volume elements. I'm going to have an integral from 0 to h dz and an integral from 0 to 2 pi d phi times rho. Rho is equal to r h minus z over h. Then I have the term that corresponds to the 1 over sine alpha. That's the square root of r squared plus h squared over h. And then I have the term that corresponds to h rho plus rz over the square root of r squared plus h squared. You can see here I took h and then multiplied by the rho, which is r h minus z over h, plus rz divided by that corresponding square root. So it's complicated, but each of the terms is simply what it is. I just have to plug them in, and then I will get the right answer. Now there's going to be a lot of cancellations here. You can see the square roots cancel. You can see that there is an h in the numerator and 2 h's in the denominator. I've got a h minus z factor. I've got a big R factor. There are 2 of them that will come out of the numerator, and so forth. I have to put all of this together, and in the end, when I do that, what I find is I can immediately do the integral over phi because it's just equal to 2 pi. That gives me a 2 pi over 3. I'm left with an integral from 0 to h dz of what is left after we simplify this horribly complicated numerator, and it ends up just being big R squared times h minus z over h. So now I have to integrate that. Well, the first term, h, when I integrate that, is going to give me h squared. And the second term, which is minus z, when I integrate that, is going to give me minus 1/2 h squared. So h squared minus 1/2 h squared is just equal to 1/2 h squared. The 1/2 cancels the 2, and I'm left with pi over 3 r squared h, which if you remember your geometry, I myself often don't remember exactly what the volume of the cone is, that indeed is the volume of the cone. To check that that is the volume of the cone, we're going to go one step further and just directly evaluate the volume of the cone from the volume integral. So we're once again going to use the cylindrical coordinates, the rho, z, and phi. I'm going to integrate the volume element over the cone. The cone runs from 0 to h dz. The rho runs from 0 to big R times h minus z over h. And note, it's very important in doing this that the rho integral occurs before the z integral because rho depends on z. So I cannot integrate the rho integral first. Second, I have to integrate the rho integral before I integrate the z integral. And then finally, the integral over the angle is from 0 to 2 pi rho d phi. Okay, the integral over phi is easy to do. That gives me a 2 pi. The integral over rho is easy to do. That gives me rho squared over 2. But rho is equal to r h minus z over h, so I get a big R squared, a quantity h minus z squared over a 2h squared. I can pull out the factor of r squared. I can pull out the factor of 1 over 2h squared. And now I have to do the integral from 0 to h dz of h minus z quantity squared. Well, let's look at each term. There's an h squared term. When I do that integral, I'll get h cubed. There's a minus 2h z term. When I do that integral, I will get minus h cubed. And then there is a plus z squared term. When I do that integral, I'll get z cubed over 3 evaluated between 0 and h, which gives me h cubed over 3. You can see the first two terms there are going to cancel, and I'm left with h cubed over 3. The 2's cancel. Two factors of h cancel with the h squared in the denominator, and I'm left then with 1/3 pi r squared h, which is indeed exactly the volume that we got the other way. You might want to argue that doing the volume integral is simpler in this case than doing the surface integral. That certainly is the case, but in some other cases, it might actually be easier to do the surface integral than the volume integral to actually calculate the volume of this object. And even if it isn't simpler, it's kind of a neat identity that we had that came from the divergence theorem. Okay, that's all that I have to say about these three problems of the week. I hope that carefully going through these integrals will help you understand how to convert line integrals into regular one-dimensional integrals or multi-dimensional integrals that we can integrate, or surface integrals, and also volume integrals, and understanding how you just go step by step and you work slowly, make sure you get all of the terms correct, and you'll indeed get the right answer.